In June 2024, as Boeing's Starliner approached the International Space Station, its steering thrusters began to fail. In the vacuum of space, several of the critical jets simply stopped firing. This was the Crewed Flight Test, or CFT, the first time this spacecraft carried humans. For the 2 astronauts on board, this mission was the final proof that the vehicle was ready for regular service. The symptoms were severe. 5 aft-facing thrusters died during the approach, and 5 separate helium leaks were detected in the propulsion system. While the immediate focus was on the failing hardware, the investigation eventually traced these glitches back through years of organizational history. NASA chartered an independent program investigation team to look past the broken valves. They were looking for the decisions made years before the launch. Investigators used a framework called a fault tree. This method maps out every possible failure mode and uses color-coded rating criteria to weigh the evidence for what actually went wrong. The tree has 3 levels. It starts with the proximate cause, the literal physics of the failure. It then moves to the intermediate cause, like missing data, and finally reaches the root cause, found in the management structure of the program. To understand why a multi-billion-dollar spacecraft failed in orbit, we have to follow this tree from the hardware in the Doghouses down to the way the teams communicate on the ground. Starliner's propulsion is housed in pods called Doghouses. These modules protect the thrusters, but they also subject the internal components to extreme heat during flight. During the approach to the space station, the thrusters fired in rapid, repeated pulses. This caused a localized heat soak that drove temperatures far beyond what the internal valves were designed to handle. This heat affected the Teflon poppets, the internal seals that regulate propellant flow. The seals physically expanded or swelled, which restricted the amount of fuel reaching the engine. The high temperatures also caused the nitrogen tetroxide, or NTO, to vaporize. NTO is the liquid chemical used as a propellant. It began to boil inside the lines, creating bubbles that choked off the thruster's ability to generate thrust. Unraveling a failure this complex takes incredible investigative work. If you enjoy deep dives into how systems break, subscribe and like the video. While the physics of the Doghouses were now understood, the investigation had to answer why these thermal flaws weren't identified during ground testing. This table summarizes failures across all flights. It shows Boeing and NASA saw these jets fail during previous uncrewed missions. 10 thrusters failed on OFT-1 and 3 on OFT-2. Because those missions succeeded, the teams didn't resolve the underlying issue. The team identified an intermediate cause, a lack of engineering data standards. Because sensors weren't recording at high enough sample rates, engineers couldn't see the specific thermal spikes happening during flight. This section of the final report explains how that missing data created a problem. Without high-fidelity recordings of the heat, the teams assumed the hardware was performing well above its limits. This led to what investigators called a false belief in the hardware's robustness. The lack of specific data didn't lead to more caution. It gave the organization a sense of confidence that the spacecraft was ready for crew. At the very bottom of the fault tree, the investigation identified root causes related to organizational factors. This is where the partnership between NASA and Boeing began to break down. The program used a model called Insight versus Oversight. It was designed to give the contractor more independence, but it inadvertently created silos where critical engineering data wasn't being fully shared or debated. Under the pressure of the launch schedule, the burden of proof reversed. The traditional aerospace standard is, prove to me it's safe. The report reveals that the team shifted toward a prove it will fail mindset. If engineers couldn't provide data demonstrating that a component was definitely going to break, management cleared it for flight, even when the flight sensors were too slow to capture the actual risk. This philosophy meant that missing evidence was no longer a reason to stop. It became the justification to proceed with the launch. NASA's final recommendations go far beyond hardware fixes. They mandate speed of trust training for leadership and new standards for how engineers and managers communicate. Modern spaceflight requires an alignment of bureaucracy that is now as intricate as the thermodynamics of the engines themselves. The failure of the CFT thrusters wasn't just about seals and boiling propellant. It was about the structures on Earth that stopped the people building the rocket from listening to the data. As we move further into the commercial era of space, Our success depends on whether our human organizations can be as precise as our engineering.